Okay, and we are back. So many of you look like you were here just a couple minutes ago. I could still do the introductions, but we're going on into the world of open possibilities, data center, liquid cooling, distribution, guidance, and reference designs. In our previous discussion, we talked about why the industry needs these and why OCP created the Advanced Cooling Facilities team to help do that. The teams that you see before, we've added one more person. We have Mr. Gross, Mr. Minash, Mr. Musili, and myself, Don Mitchell. Obviously, I could say John, and John, but I thought Mr. Gross, Mr. Minash, and Mr. Musili. And as you look through these, was more appropriate. JM Gross Engineering, for those of you who have worked with John, he's John Gross. He's an amazing resource and doing a lot of projects right now, or has some experience in integrating liquids in data centers. So we have real-life design experience and projects going on. John Minash works with Vertiv and is a solution architect. He does a lot of advising customers on all aspects. So if you did want to start talking about impedance and electrical, he could go down that path as well. But he also solves a lot of problems for people on the cooling side. And then John Musili's not only with CPS today and in Integra, but he had a very extensive career with this company called Intel. And he headed up the mechanical aspect of Intel for many years. And so he's seen firsthand the concepts of doing liquid cooling. And we were lucky to have those three attendants. I'd also like to point out that as we worked through this past year, one of the outcomes of this past year was the publication of a data center liquid distribution guidance and reference design. And one thing you should note from this, I list on the top line, you have the people who are here, and also Valerie Sorrell from Microsoft could not be here. Those are what I call my steering committee, the people that I go to for answers to validate when somebody brings up an objection or things like that. Is it a real objection or is it part of the mythology of data centers? And we work this through. But we've also had a huge number of contributors, including the famous Mr. Bean down there in the front row. And as you go through the list, people have given contributions through the past year. Jack has been a great advisor to me in many ways. And so this is not a document that was just created out of a garage by me and a couple of my buddies with a beer. We actually talk about liquid distribution in a very scientific way, or we try to. We already covered about the fact that our role is a bridge, or has been a role between data center facilities and rack and power, and we just reorganized. And we just looked at this concept here of, don't fear liquid cooling, plan for it. So if you did go into the white paper, you'd find there's a couple case studies we have, and I'm going to jump right into it. There's a case one, and then we look about beyond the design, procedures and commissioning insights, and virtual design and construction delivery. And we also then look at a couple appendices, and we're going to dance through some of those. So let's start out here. This is probably the first picture concept of what it is we really tried to capture. And early on, we said, let's get a picture, help people understand what does a deployment of liquid-cooled IT in an air-cooled IT environment look like, or what could it look like? And we came up with these three studies. So John Minash, you haven't had a chance to say too much. Can you handle the first two, which I don't know if you want to look over here or look over there?
Yeah, I'll look over, yeah. So these are reference designs that are based on just some ideas. They're not actual customer implementations, but we're looking for that. So as part of this, I'd like to just make an appeal. If you have a design that you'd like to submit to OCP for a reference design, we'd be happy to take that and look at it and scrub it and make it anonymous and put it into our bag of tricks that we make available on our website. So what we have here on the left is a cold plate type of a system with a CDU. So we've got facility water, or the chilled water loop, so to speak, which we're calling an OCP facility water. And that's going down to a couple CDU units, which are in redundant fashion here. And they are doing a couple things. They're bringing the pressures into the right ranges and also the temperature. So it's an isolated loop separate from the building system. Then the next one we have is a little similar. It's using rear door heat exchangers, but these are not going through a CDU. These are going directly from the chilled water system to those units. Now it's worth noting, your chilled water system would have to be proper in terms of temperature and pressure to be able to do that. So you wouldn't want, for example, water that's too cold and you have condensing happening on your rear door heat exchangers if they're not designed for that. So there are options, and it really depends on what you have and what you're starting with and what you'll add. And then the last one is, I think, probably most appropriate to talk about with what's been on the floor today. We have a lot of immersion technologies that have been presented here at the show. And that is a layout with CDUs, again, doing heat exchange and making a separate loop, bringing it to immersion tanks. Those immersion tanks then are rejecting the heat, and that's going out to the pump system, which is shown, so redundant pumps, and then we have dry coolers. So in this case, there is no mechanical cooling going on. There's no vapor compression cycle. There's no compressors. This is all rejecting directly to the atmosphere, something that's becoming possible with adoption of immersion and cold plates. So
Appreciate that. So that's kind of a highlight view. And we continue to expand. We spend a lot of our time breaking down the case 1 and case 1A and going back and forth on how those could work. As I mentioned before in our previous discussion on Friday, I had a head of a financial organization said that he was actually looking at case 2, where they were going to add liquids and just take a pump a pipe in heat exchanger. But then that also and we led to this in the past, it leads to the question of, do you put a heat exchanger and just air to the heat out to the environment, or you find some productive use for that? One of the key challenges you have, first off, is where do you put the pipes? How do you decide where you're going to put the pipes? What thoughts process here? John Musilli, any idea where do you put pipes?
Well, of course, new construction's relatively straightforward. You route them on the exterior or above, in a protected area, or underground, under the plates, under the floor. If you have to go into a retrofit, same thing. You keep them relatively low. I've used cut-in duct, walker duct, we cut in channels and keep everything low and just bring up lines to where I need them. It's just being smart on how you do it. And part of the paper that we worked on on this team, it talks about how to mitigate some of this risk through good design and good commissioning and good construction practices.
So one other slide we came up with was this one here. And it's kind of interesting. When I first came up with this slide, people said, what does it mean? And then someone else said, you're getting too technical. But talk through this one here, John Gross. What are your thoughts?
Yeah, so one of the things that I wanted to mention before we go too deep into this presentation is the goal of the work stream was not to create a bunch of brand new content when there are a lot of other recognized organizations out there that have generated content. So wherever possible, our focus was to take best practices from other organizations and consolidate it into a centralized guidance. We leveraged a lot of ASHRAE content, specifically ASHRAE TC 9.9 content, when we were working on the work stream. This one here actually leverages a bunch of information from the ASHRAE 90.1 energy standard. So the concept behind this chart is to give people a quick look. This is not an engineered solution or an absolute requirement, but it's basically to give folks an idea of, at a given pipe size and at a given temperature delta on your system, I could potentially reject X amount of heat with this pipe at this delta T. Now, you can't come up with capacity if you only have delta T. You have to have flow rates. So where do the flow rates come from? That's where we link back to ASHRAE 90.1's energy standard, which actually has a chart of flow rates based on a given pipe size as a maximum allowable under the energy standard. So we basically use those flow rates combined with the delta T range that you see here to get capacities. Now, one of the things that I want to mention also is we go as low as about, 7.2 degrees Fahrenheit.
4 degrees centigrade.
4 degrees centigrade, and we go up from there, and I think we stop at
16 and 10.
Sorry, thank you, 18 and 10. And the reason why we didn't go any lower than 4 degrees centigrade is because, one, it's very rare that people are going to go to that low of a differential temperature on their system. The reason we stopped at 10 degrees centigrade is because When we look at a lot of retrofit applications, right? We're not talking greenfield construction purpose-built, we're talking retrofit applications. A lot of existing facilities that are out there are gonna be looking at modifying systems that have chillers attached to them. And chiller systems are not going to be doing delta T's higher than 10 degrees centigrade without a CDU in place.
Fantastic. A couple things you got from this conversation. Number one, we partner with ASHRAE. John, how do we partner with ASHRAE? Do you know anyone that works with ASHRAE?
Not a clue.
Okay.
I'm fortunate enough to have been involved with ASHRAE TC 9.9 for the last few years, and I'm one of the current voting members of the technical committee.
And we also have people like John Bean, who's been involved, and he's given some insights as well and things like that. We are not competing. We are partnering with them, bringing their information. Number two, I've had people that looked at this and said, that's way too detailed. But guess what? One of my former systems engineer, Jason Rafkin, is now a vice president for solutions architecture at a company called Stack. He's looked at this and he said, thank you. This just gives me a quick ballpark. I look at this and I see that for a 6-inch pipe with a 6-degree delta T, I can do a megawatt, okay? That's what I'm looking at, 6 degrees centigrade. So that kind of gave him a thumb rule that it was 6-inch or it goes with an 8-inch and you can get a little bit more. That gives him a capacity number for his starting point of reference. Because John is a rental, MTDC rental data center owner, and he's going to customers and they're saying, I want to put in a megawatt of cooling. He's got to figure out how big the pipes are, where they're going. These sort of things help him. This does not put Mr. Gross out of business.
Thank you.
Because I can trust you that John Gross is still going to have to do a lot more than you see in here, but it just gives him a starting point. And that's what we're trying to do with the industry, make them understand where they're going to start. The next step, I should have relabeled this, perfect prefab at the speed of thought, okay? Back in the 90s, end of 1999, this guy named Bill Gates, some of you might have heard of him. He wrote a book called Business at the Speed of Thought. And what he was talking about there is how the digitization of the communication processes of our world had made it so business that used to happen in 7 days could now happen in 7 minutes. Literally that. It took me 7 days to get a sales proposal out to people in 1992. It took me 7 or 17 minutes to do it in last week, okay? I already had it down. I could email and stuff like that. I don't want to go through the logistics. The same parallels can apply with data center delivery if you observe some requirements. Now, what kind of things make us get close to business or perfect prefab at the speed of thought? What do you need? I'll go ahead and start with John. You've been, Mr. Massili, sorry.
Well, the other two engineers on the stage, they're much more detailed about this than I am, but I look at it more conceptually, and I say my objective is to get as many pieces built in a well-lit, well-trained environment and get them shipped in to me so I can assemble them anywhere in the world. Because I've had projects globally that the language skills are not the same as mine, and the literacy skills are not. So prefab and literally tab A, slot B, blue to blue, red to red, have a huge advantage in data center infrastructure, sophisticated data center infrastructure.
John Minash?
Yeah, I'll add, I think in this case, anything done in a factory potentially can have a lot higher quality than you're going to achieve on site. And consistency, right? So
just kind of make it personal for you. You work for a company called Vertiv, right?
I do.
Do they just send a bunch of parts and have trained construction people put it together, or do you actually play with prefab in some of what you do?
Yeah, we do a lot of prefab, and there are a host of reasons why prefab may or may not work for a given client data center. But one of the benefits is, again, the factory environment. We can control our quality, document our quality, and test quality, which is hard to do on site with trades. Regardless of the skill level in the general area, that does vary widely, and there are areas where we can't count on that, but we get consistency in the factory. And again, repeatability and scalability. A good example I always think of when I think of modular building is take a modular home building. Very often the framers are going out there in the rain. Well, they're not going to do as great a job potentially in the rain as they are, or getting snowed on, than they are in a lit, warm factory. Coming in and doing their job. So I think there's an advantage there.
And the other thing that I would throw in there quickly is, I think everybody in this room that's involved with our industry recognizes the constraints that we have with supply chain right now, and the time impact that that's having on delivering data centers. And as we all know, time to market is huge for pretty much everybody in this room. So one of the things that prefab gives you is the opportunity to be doing a lot of parallel construction that's not necessarily all happening on the same site. If you can modularize your cooling distribution or your power distribution, skid package it, put it on the back of lowboy 18-wheelers and be having it show up pre-manufactured, ready to slide in the building as the building's getting dried in, then you can help to overcome quite a bit of the supply chain issues that we're having right now.
So tied into that, one thing I'd like to highlight, pretty much everyone in this room, if you've been in the data center industry 10 years, you've heard 10 years of BIM and prefab are the vision of the future. 10 years ago, I went to conferences and people said BIM and prefab are the vision of the future. Last year, and today you're hearing the same thing. I actually went to a conference 2 years, just before COVID, and I heard that, and I put my hand up at the end of the presentation. I said, hey, you guys were talking about this 8 years ago. Why isn't prefab taking over the world? And you know the number one answer I got? The pipes don't fit. Because you have put together a prefab assembly, you try to get it to site, it settles a little bit, you don't have alignment, or something else happens, and the pipe, this was one of the things that was brought up by someone on the panel. Now, at the end of the day, one that we did look at is the concept of adaptability and prefab of pipe. And the other thing also to kind of extend the scope, what you're seeing here, is prefab is a generic term for a wide range of concepts. You want to kind of unpack that a little bit, John, Mr. Masilli there. What are we looking at there?
So you could start with things that are as small as a bread box, literally, right? Just a little VAV, it's going to go up in a ceiling somewhere, it's got its electrical connections on it. And then you could go all the way up to full, 600,000 CFM air handlers that'd all be in a couple components, but could be bolted together on site and online within 2 or 3 days. You could have electrical modules, that could be trucked in that are in the 2 megawatt category. And to the point earlier, you don't have to have your pre-built electrical room, bring in that equipment and its conduits. These units could attach to your facility in literally 3 days through a junction box, and you're up and going with 2 megawatts of power, or 10, or whatever your configuration is. Yeah. So it's the quality control is important in the testing, and also when there's an error, because there will be errors, they're generally very consistent in the factory. It's usually a drawing error or a single individual doing something wrong. You could back up over that person's work or that drawing and go back and make all those corrections, as opposed to 10 different electrical rooms having 10 different workers in them.
And I think also the assembly on site is a big piece of this as well. There's so much data center construction going on right now that I think, anytime we talk to any of the contractors, everybody is stretched thin. They're having trouble getting pipe fitters, they're having trouble getting electricians, and so on and so forth. So one of the projects I'm working on right now, where we're looking at prefab, we looked at 1 row of piping distribution for a liquid-cooled application. And if everything is built, stick-built in the field, we're looking at, I believe it was approximately 180 joints that had to be made up down the length of the row. If we prefab it, ship it to the site on skids, and hook it up in the field, it's 8.
So that's a common impact. One of the things, again, I go back to the concept 10 years ago, people were talking about BIM and prefab as being the vision of the future. Guess what? It wasn't until 2013 that construction grade BIM really started to be defined, okay? So people knew that the concept of building information management or things like that was a concept, but it was in 2013 where you had the LOD concepts and people started making it something that was more of a standard. And today, what we're looking at, one of the key things we've been pushing the data center providers or the vendors that are parts of OCP is the concept of the obligation to provide content that a contractor or an engineer can use to deploy your products. If you make an immersion-cooled product or a cold plate or any product, your choice is either having every one of the engineers that work on your projects model what you've done and pay Mr. Gross to do that, or you do it one time and they all they could get the benefit. John, could you explain that a little bit better than I did? I don't think you do a much worse job. Give it a shot.
So the challenge when we're trying to do design is that we're trying to design faster, we're trying to design smarter and more efficiently, and we're trying to hand off work product to the contractors that is more construction ready. Is it full-blown shop drawings? Typically not, although I do have projects where we're paid to do that. But the gist of it is that in order to do those high quality, tightly coordinated design drawings, we need content that's dimensionally accurate. Okay, that doesn't mean that we need to know where every single punched hole is in every piece of sheet metal in the rack or in the tank or so on and so forth. We need to know the geometry, the rough dimensions, or not the rough dimensions, but the precise dimensions of the length, width, height, and clearance. We need to know the locations of where the pipe connections are, where the power connections are, where the telco connections are. Outside of that, geometrically, we don't really need much. There's some other parametric data that we'd like to get in there that's listed here in the slide pack and also in the white paper, and I don't want to go too deep into that. But what we frequently get from manufacturers is their step file from fabrication, right? The 3D file that goes into the machine that punches all the holes and everything. The 3D software that is typically used by many design firms in the industry, every single little geometric shape that is in that piece is getting rendered by the GPU in that workstation. So if you've got 378 holes that are punched in that sheet metal, the software is going to try to render 378 holes. And if none of those matter, all you've done is bloat the file size, slowed down the software, slowed down the process of the design firm, the design engineer. Autodesk actually has a recommended standard that the files, the Revit family files that are used for this content are between about 500 and 700 kilobytes in size. And on a recent project, when we had the first ask from the manufacturer for some Revit content, we received a file that was 25 megabytes. We've got some pretty heavy-duty workstations at our office that run liquid-cooled and very heavily overclocked. We tried to import that thing into the model, and it completely shut down the workstations.
Is this on? Okay. So I got a surprise speaker in terms of, he's going to be surprised. John? Tell me a little about your background here, John. Did you ever work for any company that did cooling solutions and actually had BIM content in it?
Yeah, we did. Probably 80% of the product that we developed in the last 7 years, where a company that I left, we had BIM models available.
Okay.
What we did do, though, is we're always worried about continuous evolution. We did not put the BIMs for people to download autonomously on their own. We made it that you'd have to come in and request to get the most current up-to-date BIM, because as manufacturers change whatever, you may find the worst thing to do, the one thing worse than not having a BIM file, is giving somebody the wrong one. That is probably actually worse.
Right. Yeah, I completely agree with that. And I've seen a mixture from manufacturers of they don't have it at all, or they have it upon request for rev control, or it's published online and you're hoping it's the latest and greatest.
Yeah. So, go ahead.
I'm going to say, if you're a manufacturer and you're sitting there wondering how do we produce Revit or BIM files, Revit is the probably preliminary or primary software that's used. The answer is I would go to an expert. You know, don't just rely on your own internal engineering teams, because the skill sets are the same, but the programs are so different from SolidWorks or any of the other 3D modelers that they're going to probably do it wrong a few times. And I can tell you, as both somebody that's produced those and that consumes them quite often, there isn't anything worse than a model from a manufacturer that's bad, right? I'd rather go and grab a pump out of the generic database that's provided with the software, Revit, than get a model from a manufacturer, and it could be the kind that John just suggested. It's way too detailed. It was just a straight export from their solid modeling program, and every little washer is being rendered. But
I've seen every single thread on every bolt rendered.
Yeah. And the other one is that the dimensions are wrong, or they didn't pay any attention to that. They spent all their time making it look good, right? That's not what you're looking for when you're doing BIM modeling. You're looking for overall dimensions, accuracy on where the connections are, and the different types of systems: water, power, network communications, all that can be put into these models. And I think a big benefit of this is if you've ever worked in construction, a lot of the processes are contingent on each other because you're waiting to get a set of drawings. So the electrical people aren't going to do some stuff until the mechanical people are done with their ducting, or vice versa. With Revit, these things can be done simultaneously and synchronized so that collision detection is a problem. If you've dealt a lot with 2D drawings, you can spend a heck of a lot of time looking at 2D drawings, trying to figure out if the plan view is the same as the other orthographic, the elevation from the sides, for example. And if they're not, it doesn't stand out necessarily. A lot of errors from that.
The last thing I want to throw in there, Don, 10 seconds, is, John mentioned there's consultants out there that specialize in doing BIM content development. Typically speaking, to develop an immersion tank or something along those lines to the level that the industry is looking for, you're probably talking about maybe 10 hours worth of contracted time at somewhere around maybe $100 to $125 an hour. So under $1,500 as a manufacturer, you're getting a BIM file for that product. So that's a big thing for an engineer. If we've got 20, 30 different products on a project, we can't afford to go out and pay the consultant to do that. But as manufacturers, if you've got a catalog of maybe 10 products and you're selling these things for a $20,000, $30,000 profit each instance, then that's a different scenario.
So tied into this, and we're not saying anything new. If you've been around for 10 years, you probably heard this at other presentations. What we are saying that might be a little bit new is, as part of the cooling environments group, our recommendation for vendors to have OCP ready will be that BIM content be available. So if we need to follow up on this, we can follow up on this. It's not meant to be harsh. What we're trying to do is keep customers from having to pay $1,500 multiple times. And if you just do it once right, then the process is not just the cost, it's the time. If he has something that he can get very quickly, get 3 sets of drawings, go to a customer, we have some customers even in the room, and show them some comparable drawings, decisions are made quicker, delivery of those systems are much better. So that's all we're going to cover on this topic, because it's just one of many boring topics that we have waded through in this project. It's the path to doing a really good job is getting the details straight, and it starts with BIM. Another aspect, we talked previously about the concept of killing myths. In the previous introduction, we started about talking myths versus science. And we briefly mentioned this term called FMEA. And FMEA, this is actually something I also should probably handle. The first time I heard the FMEA was from this man named John Bean, okay? Now, it's been around for multiple years, but I'm gonna let someone else who's got a mic in front of them describe FMEA. Which one of you guys want to pick up the FMEA discussion?
Go ahead, John.
Yeah, sure. So FMEA is a detailed, or I should say it's a methodical way of looking at and putting your risks down in lists, with different parameters that you're listing for maybe different classifications of types of errors that you could have, and looking at them with some science, and saying, what is the effect, for example, of having a leak in a different area of the data center, right? So a leak, for example, leakage is the topic, and you're looking at how to assess your piping. You might consider a small leak in your mechanical room that's just weeping off of a valve, not as big a deal, for example, as that same valve dripping over equipment, right?
So let me pause this real quick. A key aspect of why we're bringing this up, our next discussion set is going to be people talking about leak detection, okay? And if you look at some guidance on data center design, they'll say everywhere you put a pipe, you need to put leak detection. One of the things we're trying to say is you don't want to kill myths by over-designing. Mm-hmm. A lot of people say one of the key challenges of liquid cooling is it's too expensive. It's too expensive if you over-design it. If you properly design it, there's a lot of stats, and John Gross has a lot of information that says it doesn't have to be as expensive. And one of the classic areas is if you use FMEA, if you use analysis to determine where your risk factors are and drive, maybe put extra protection in the risk factor area and drive, you don't necessarily have to overpay to build your data center.
Yeah, let me give you, I get a real life example of that. Intel was big on FMEA, and they're pretty smart people work there. So we had a data center that had overhead cooling, and we were running 16,400 GPM through that room, and it was all overhead, vertical and overhead, when it was all said and done. We went round and round and round about leak detection, put diapers on, put sensors on, put indicators on, put this, and when we finally came down to it and we thought about it, correctly, we said the highest risk was one server rack, and this particular facility happened to have thousands, so one server rack. And the other thing was that most of those leaks are going to take place and be leaks, not catastrophic failures, so they're going to be sprays or something else. They're going to be in this particular configuration, they would be in the hot aisle, and just the server fans themselves are going to push that moisture into the hot aisle. It's not going to get re-involved in the server, or very little damage is going to be done to the server, if any. So the whole thing was a mop. You fix it with a mop.
The way that I like to think about it is it's basically a weighted analysis of risk and consequence, right? So you have different levels of risk for different events to happen. That ties into the MTBF. How likely is an event to happen? And then if that event happens, what is the severity of the outcome? If it's something that's likely to happen and there's really no consequence to it, is it really something that you worry about? Likewise, if it's something that is extraordinarily unlikely to happen but it takes down the entire data center, those things you have to evaluate differently. So this is applying a scientific methodology to determine where you place your money and your investment in risk mitigation.
Yeah, so you look at these mitigating risk factors. You can not over-design, but optimize design is one way to look at it. You can increase MTBF. You can, where MTBF can be applied, you look at how to use components that are more reliable. You can improve detection. If there's a place where you think there's a risk factor, then you improve the detectability. You might make it so that you can actually see something that's hidden, or you can put cameras, or you can put leak detectors. You can set up procedures. There's a certain number of things in operating with liquids that will inherently have a risk factor unless you take it out by procedure. The process of adding a liquid-cooled IT or taking off a liquid-cooled IT, you can make that, and as you walk around the hallway, you'll see people have developed machines to pull up the device and put it back in. Someone may say you can't use, I've heard other people say immersions are messy. Immersion cooling isn't messy if you have a procedure to make sure it's not messy. If you try to work with immersion cooling and you don't have a procedure, it can be messy. It's just the way it is. So that's one of the things you do. And then isolation strategy. If you think there's a potential risk factor, you make sure you can isolate it. Any other comments on this slide?
Now, the key is there's usually a solid mitigating practice that can be done or designed.
I'll add that a big advantage to using FMEA or a similar technology or similar methodology is separating fact from folklore. Mm-hmm. Every industry has its folklore. I had this happen. This always happens. Well, as manufacturers, if we have problems, we fix them over time. And I think that never really gets factored in. So you really want to look at it from a data perspective versus a gut feeling in this case.
So I came from an industry that was somewhat risk averse. It's called the submarine industry. I lived inside a welded pipe. I was a QA officer on a submarine. Back in 1963, we lost the USS Thresher. 129 people perished. Admiral Rickover at the time, he didn't say that we lost those people because of a broken pipe. He said we lost that people died because of a failed philosophy of holistic engineering, vertically integrated quality control, and certified inspection. And by that, what he meant was holistic engineering. The short story is there was a brazed pipe that separated, we'll take that offline. Anyone who wants to hear this Thresher story, I'll tell you. But just putting a piece of pipe together is not a holistic solution. It doesn't accommodate for movement, it doesn't accommodate for alignment, it doesn't accommodate for vibration or any number of things. The vertically integrated quality control, as a sub-safe program was put in, everything that was mission critical on a submarine associated with the integrity of a submarine became sub-safe. We could track down the quality testing that was associated with every product that was put in the sub-safe piping solution. We could go back to the manufacturer date and place of origin and see the quality test. And the third aspect was a certified inspection process, a process of actually looking at the components and verifying that they were properly installed and they would achieve their mission with integrity. So those sort of concepts, that theme of SubSafe is something that has permeated our discussions as we looked at different ways of joining IT equipment. And that's they had me talk to that because it's part of my religion. So we'll go with that. So let's kind of talk about, and I think we covered this a little bit before, but good design is key, but just part of success. Can you have a perfect design? We've kind of talked about that, but let's expand a little bit more about what we're seeing here with the relationship between commissioning, MOPs, SOPs, EOPs, and design.
So as a design engineer, I can tell you that every single contractor out there will tell you there's no such thing as a perfect design. As an engineer, though, I can say that that's true as well. So but the reality of it is to execute the best quality project that you can for the owner for the life cycle of the project, you have to have a good design concept. You have to have good design documents. The design has to be linked to the operation both during the design phase and then also during the commissioning phase. Purpose of commissioning, right? If you go back and you look at commissioning as defined by ASHRAE and Guideline 0, the purpose of commissioning is to ensure that the facility's systems operate in a manner to deliver to the owner systems that operate per the owner's project requirements. Doesn't necessarily mean that they operate per the design documents. It means that they actually deliver the OPR to the owner. But once the design team leaves, once the commissioning team leaves, you have to have the knowledge base there to make sure that the facilities and the systems can be operated per the design, per the commissioning. That's where the MOPs and the EOPs come in. And quite frankly, what I see a lot, which I think is a big breakdown in the industry, is the MOPs and EOPs are written at the end of commissioning, at the end of the project, and they're never actually tested because the only time we really ever have to test them is during commissioning. They need to be developed during the design phase, during the commissioning phase. They need to be tested during the commissioning phase, edited and retested until everybody feels like they're not missing anything.
So are there people that actually get employed to do commissioning?
Yes.
Mr. Masilli, can you speak to that?
They do, and they find things, and sometimes they miss things. But the key is that it's a methodical process, and at least if you have your testing organized correctly and you know the system designs and requirements, and to John's exact point, that it's working the way that intended to work for the owner, that's key. The good news is that if it's methodical, you have a checklist, and your checklist will indicate if you've missed something. So you could always go back and do that. But the SOPs are often done after the fact and by very technical people and not the people doing the work.
And they may be people who never actually set foot on the job site and worked on the systems.
Yep.
So, John Masilli, what's your daytime job again described?
Sometimes commissioning, there's a building not too far from here that took quite a bit of my time, the last 400 or 500 hours. But the key to that was there was several errors from engineering on down, including installations. Engineering, there's several errors that were engineering, several errors that were installation, and then some were workmanship. And those will get picked up. But I think for this group, that why we're here today for the OCP and these reference designs, the key I think that maybe we're missing it because we're getting some details, is that hopefully when we're done with our work products, and our work products are almost done for these two subject areas, you could feel comfortable that this is not a big heavy lift. This is something that's standard industry practices. You just got to pay a little more attention to it. And if the industry, some of the industry or some of the owners that are manufacturers that are here, set up the BIM stuff and set up these kind of cookie cutter, even though we're calling it cookie cutter, we do want to be able to repeat it and repeat it successfully, but it's a sophisticated cookie cutter, at least at this point for immersion. 5 years from now, it's just going to be run of the mill.
Yeah, the way that I like to describe it is we're not actually really doing any new technology with the deployment of liquid cooling. What we're doing is we're taking proven technologies and we're using those technologies in new applications and packaging those together in a way that we've not really done before, particularly at scale. So what we're learning right now is what are the things that we need to take into account when we apply this technology in this manner with these other components playing into it.
Yeah, if I may, In addition, we were talking modular a little earlier. The idea of modular anything could be modular construction of a building, but I also be talking about components within a rack or within a piece of equipment in a rack. This idea, having SOPs and MOPs implemented and managed in your organization, it becomes easier the more you replicate the same thing over and over again. You're not writing an MOP for every different piece of equipment that you've implemented in the space.
Yep. So as people heard me talk earlier, I lived on a submarine. At the entrance to every space, there was a stack of MOPs and SOPs and EOPs, especially EOPs, that were available so that you knew in the case of something happening, what to do about it. And those EOPs were developed as part of the commissioning process way back from the beginning, worked through. And guess what? Because it was a standardized process, when somebody found something that was wrong with a procedure, you didn't just skip that step. You would investigate why that procedure was wrong, you'd correct that, and then the next time, and so as much as you can make this replicable, the better success we're gonna have with the liquid cooled in data centers. So that's one of the general guidance there. Got one more technical slide real kind of quick, and John Gross, I might let you, this kind of ties into some of the things you said before about you liking ASHRAE.
Yeah, so as I mentioned before, I'm part of ASHRAE TC 9.9, and one of my colleagues is here in the audience, and Paul worked with us on this as well. So as part of version 5 of the thermal guidelines this last spring, there were some significant changes made to the ASHRAE W classes, which is our temperature classes for liquid-cooled environments. One of the first things that you'll notice if you look at these, if you're familiar with the ASHRAE classes, is they used to be W1 through 5. It's now W17, 27, 32, et cetera. That was done for 2 reasons. First and foremost, at least in my opinion, first and foremost, is even those of us who were involved with writing the document could never remember what temperature was associated with each class. So this is kind of our cheat sheet, if you will. The other thing is, if you're familiar with V4 of the thermal guidelines, there were 5 temperature classes. There's now 6. So it came up from input from the industry and the folks particularly selling and building in EMEA. There was a need for a temperature class around 40 degrees centigrade. And so that fell between W3 and W4. And so, the first question that came up is, what the heck do we call this thing? W3.5? That sounds kind of silly. So by changing to this standard nomenclature that allows us to add and subtract W classes as the industry evolves, because I think we can all agree we're in a very dynamic portion of the lifespan of this particular industry. So with this, we have the temperature classes denoted here. One of the other things that was written into the thermal guidelines that OCP supports is that there was a clarification of the definition. Previously, if you had a W3 solution, which by the way corresponds to 32C, all you had to do to have a W3 solution was to be able to operate your equipment somewhere up above the upper limit of W2, which was at 27C. So if you operated at 28, technically speaking, you were W3. That definition has now been changed, which is to help align with what the facility is providing with the FWS solution, ASHRAE's term for your primary cooling loop. And that is, if you are a W32 compliant ITE solution, that means your ITE can operate fully unthrottled all the way up to and inclusive of 32 degrees centigrade entering fluid temperature from the FWS. Operating there but having to throttle down 10% does not count. So that has now been clarified, and it factors into the SLA conversation because as a facility engineer working with with operators, we'll design a loop to supply W32 water, and if we're supplying W32 water and the ITE can't keep up, then we've actually still met our SLA requirement from the standpoint of providing a liquid solution that should work with that ITE.
So there was a lot of discussions on SLA. One other thing I would like to highlight is on the slide next to it, we have this dew point limits per ASHRAE. And one discussion that we had that ended up being rather controversial with people at one point was, should you keep your pipes temperature, or the liquid in your pipes going above your racks, above dew point? You want to expand on that a little bit more? Do you, first off, is it our opinion or is this an ASHRAE opinion also?
So that's becoming an ASHRAE opinion.
Okay.
I don't know that we've actually formally put it in any documents, but it's something that we're discussing as we're working on some updates to other publications right now. But operation above dew point is definitely something that will help the overall operation of the facility. Again, going back to the fact that the vast majority of the water introduction that we see coming off of pipes is not actually from a leak where you're having water leave the inside of the pipe and go to the outside. It's actually condensation coming off the pipe out of the insulation and so on and so forth. So by going up above dew point, you get rid of that risk. So that's one of the things that we are focusing on is operation above dew point, again, to minimize risk.
Well, and so that point, it's not, and we had a very senior engineer that said, to my point, I can design with insulation and make it so you can operate above with your cool liquids below dew point. The issue ends up being what OCP is trying to do is make it simple to deploy at scale. And there's, it's easy enough. There are ways to work around it, and that's kind of where we're going. And I thought I did see a reference from ASHRAE TC 9.9 that said recommended keeping 2 degrees centigrade above dew point, but I'll have to check a look at that one.
Yeah, we did some kind of last minute updates to the book, and I know that was talked about. I can't remember if it actually made it in there, but I think the other piece of this that OCP is trying to hit on is going back to that conversation of design, construction, operation, commissioning, et cetera. I think a lot of engineers out there know how to design systems that are insulated and can protect against dew point. We got vapor barriers, we got specs for all that stuff. Contractors will build it. I don't think we've ever seen a maintenance personnel run into a piece of insulation and damage the vapor barrier, and a couple months later we're seeing staining all over the place and water dripping on the floor. That never happens. So the idea is if we operate above dew point, yes, you can design it perfectly, you can build it perfectly, and you can still stay there and not have to worry about the risk coming down the line as the building ages.
Okay, so we're just about out of time. Call to action is very similar to what we had before. We'd like to have people participate. These documents were not created in one call. We have actually had 60 calls, over 60 calls in the past year, where we've had engineers from Europe, from engineers from Asia Pacific, engineers from North America give feedback and comment. And the documents are posted in a Google Docs, and people can make editorial comments and such. So there was a certain amount of consensus here. And one of the key points ends up being pretty much everyone who's doing liquid-cooled IT, their equipment can operate successfully well above dew point. So why shouldn't you make it happen that way is one of the kind of ties in what he said. So we'll call this close right now. Are there any final questions on today's session? Mr. Harrington.
Okay, I just wanted to talk about the dew point. I'm sure you guys already talked about it, but obviously if you run the processor colder, you save energy. So if you maintain all the liquid cooling systems above dew point, you're just missing out on that energy savings.
The phrase obviously is more efficient to run below colder. I don't know, is that true?
Well, I think when you look at it from a holistic standpoint, you know, from the cooling system all the way down to the chip, the processor can definitely provide more compute throughput the colder it's run. You reach the break point where in order to get to that colder fluid temperature, you're going to have to start bringing compressorized refrigeration back into the conversation. Yep. And so there's a lot of technologies that are out there that are refrigerant-free and compressorized free, where you can drive the dew point down, use of desiccants and so on and so forth, where you can actually still run a cold loop but still have the dew point low in the space below your fluid temperatures.
Okay, what I was getting at is the point of running the data center as cold as possible using the cooling tower only, just the whole time. So that means your cooling water temperature changes with the outside.
No. I think one thing we're not talking about running the data center as cold as possible. The air-cooled IT can operate at at the temperatures you were still doing the air-cooled. What we're saying is the liquid going to the rack solution set should be above dew point.
Well, and so I think where Steve's going with it is not the air within the air temperature within the data center, but the fluid temperature within the data center, trying to run that fluid as
Sure.
cold as possible within the confines of staying outside of mechanical refrigeration. And I agree with that, but part of what we have to be considering when we look at it, at full deployment wherever it happens to be in the world is there's a wide range of wet bulb temperatures that we have across the locations where these are being deployed. So that range of temperatures swings around quite a bit. But again, I go back to the statement that even if we're doing, say, a cooling tower only solution, right, and we're able to run off that cooling tower, let's call it 22, 21 degrees C water that we can send then to the processors, you can still use something along the lines of desiccant dehumidification to drive your dew point down into the teens centigrade without using mechanical refrigeration, get rid of the insulation, get rid of the condensation risk. I think John's calling our time here. Yeah.
One quick comment. This is Paul Artman from, I was founding member of TC 9.9, but John did a really good job on discussing the new W ranges for water. And we've done a really good, as an industry, saying this is why you want to transition from air to water. What we have to be extremely cautious and start working on is saying that W45 is probably not viable. We've got to say, we're moving from air to water, but power is going up in such a high CAGR. You just got to be real careful about what do we think of the recommended ranges is, because I would never advise anybody to do W45. That's kind of where we are in Europe today with some HPC's deployments. And that's on 300 and 400 watt CPUs, and we're talking 1,000 watt GPUs. But I think that's the extra level of detail that we need to do is we got to go to water cooling, just like we went to free air cooling in A4. We scale pretty well because CPU is flat, but we're in a very high CAGR on power, and we just got to be cautious about. Clearly, W17 does make sense for being green, but we also have to be cautious on saying that W45 is going to be really difficult to extend out, for long periods of time.
So a couple things real quick. And we do have to leave. Number one, what ASHRAE does is what ASHRAE does, and we reflect that. So what you're bringing up to a large extent is something that ASHRAE should make the recommendation of. And we're never going to go back to ASHRAE and tell them how to do their job. Number two, I would like to highlight that this recommends, ASHRAE's current recommendation for dew point is about 15 degrees centigrade, okay, for the recommended regions, okay? As far as I know, is that correct? Mm-hmm. So we can have these discussions offline. I'd be more than happy to encourage. I'd really like to talk to Steve a little bit more, but we actually have to call this a little bit clearer. Okay? Thanks.
Thank you.
Thank you.